Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to learn 11th module, 5th lecture, that is 55th lecture of this course. Again, as I spoke in the previous lecture, we are going to do some worked out examples so that you would be able to get familiarity. The first and foremost example which we could see, and we have done enough examples, but despite of that, still we need to get some familiarity over the matrix computation. The first example is, let us consider the singular value decomposition of the following matrix. Let's say I have 710055 and this is the matrix. Here we are trying to find out two solutions using A times of A transpose times of A. Here we are trying to find out two solutions using A times of A transpose and A transpose A. First solution using what we call A times of A transpose. For normalized vectors Ui, A times of A transpose is equal to 50, 0, 40, 0, 0, 0, 40, 0, 50. To find the eigenvalues of A times of A transpose, you will have the absolute value of A times of A transpose minus lambda is equal to 0. So you will have the determinant of 50 minus lambda 0, 40, 0 minus lambda 0, 40, 0, 50 minus lambda is equal to 0. And when you expand this determinant, 50 minus lambda times of minus lambda and 50 minus lambda minus 0 times of 0, minus 0 times of this 50 minus lambda. So ultimately when you do it, it would be equated to 0. Similarly, this 50 minus lambda, from here minus 50 lambda plus lambda square, and this is anyway 0, this is 0, this is anyway it is 0. 40 into minus 40 lambda, minus minus it is plus. So you will have minus 2500 lambda plus 100 times of lambda square minus lambda cube plus 1600 lambda is equal to 0. Then I will have minus lambda cube plus 100 lambda square minus 900 lambda is equal to 0. Minus lambda cube minus 100 lambda square plus 900 lambda is equal to 0. So the simplification turns out to be a cubic equation. So this is again minus lambda cube minus 100 lambda square plus 900 lambda is equal to 0. Lambda times of lambda square minus 100 lambda plus 900 is equal to 0. So lambda is equal to 0. So lambda is equal to 0. And lambda square minus 100 lambda plus 900 is equal to 0. So you get this lambda is equal to 0, 90 and 10. Eigenvectors for lambda is equal to 90, you write it as A times of A transpose minus lambda I, which is nothing but 50, 0, 40, 0, 0, 0, 40, 0, 50 minus lambda is 90, 90 times of 1, 0, 0, 0, 1, 0, 0, 0, 1. So this can be further simplified to 50, 0, 40, 0, 0, 0, 40, 0, 50 minus 90, 0, 0, 0, 90, 0, 0, 0, 90. So which turns out to be minus 40, 0, 40, 0, minus 90, 0, 40, 0, minus 40. So now reduce this matrix R1, that is R1 is equal to minus 1 over 40 times of R1. So that means it would take into this form 1, 0, minus 1, 0, minus 90, 0, 40, 0, minus 40. And R3 minus 40 R1 is R3, that is 1, 0, minus 1, 0, minus 90, 0, 0, 0, 0. So again I do it because this one I wanted to make it as a 1. So minus 1 by 90 times of R of 2. So that takes into the form 1, 0, minus 1, 0, 1, 0, 0, 0, 0. So this would become the system associated with the eigenvalue lambda is equal to 90. It becomes A times of A transpose minus 90I multiplied with x1, x2, x3. That would be 1, 0, minus 1, 0, 1, 0, 0, 0, 0. Multiplied with x1, x2, x3. So which would be equated to 0. So essentially you do get the values 0. So x1 happens to be 0, x2 happens to be 0, x3 happens to be 0. Let x3 is equal to 1, then eigenvector corresponding to the eigenvalue lambda is equal to 90 is given by like this. So v1 is equal to, that is 1, 0, 1. Similarly, the eigenvector corresponding to the eigenvalue lambda is equal to 10. So that is v2 is minus 1, 0, 1, and the eigenvector corresponding to the eigenvalue lambda is equal to 0 is like this. So v3 is equal to 0, 1, 0. So normalizing the eigenvectors, we do get the matrix as u1, that is v1 upon norm of v1. So it is 1 over 1 square, 0 square, 1 square, 0, 1 over 1 square, 0 square, 1 square. So this is 1 by root 2, 0, 1 by root 2. So essentially this becomes 0.70711, 0, 0.70711. And u2 will become, u2 is equal to v2 upon norm of v2, that is 1 upon square root of minus 1 square plus 0 square 1 square, 0, 1 upon 1 square 0 square 1 square, and here it is minus 1 over root 2, 0, 1 over root 2. So which turns out to be minus of 0.70711, 0, 0.70711, and u3 will be is equivalent to v3 upon norm of v3, that is 0, 1, 0. Therefore, the singular value decomposition using the solution is A times of A transpose is given by U times of sigma V transpose, where this sigma is equal to the diagonal values, rest are all zeros. So this can be written simplified to, that is square root of 90 is, that is 9.48683, and this is 3.16228, this is 0 and this is 0, and u is equal to, that is u1, u2, u3, and this is equal to 0.70711 minus 0.70711, 0, 0, 0, and this is 1, 0.70711, 0.70711, and this is 0. So V is found using the formula, that is Vi is equal to 1 over sigma I A transpose Ui, where V is equal to this matrix, that is 0.89443, 0.44722, 0.44722, 0.89443. Second solution using A transpose A for normalized eigenvectors Vi is, this is the matrix A transpose A is 7 0 5 1 0 5. So this is that is 3 rows 2 columns 7 1 0 0 5 5. So ultimately it turns out to be this matrix 7 4 3 2 3 2 and it is 2 6. To find the eigenvalues of the matrix A transpose A, so that is A transpose times of A, which will be equal to absolute value of A transpose A minus lambda I is equal to 0. So you get 74 minus lambda 32, 32 26 minus lambda is equal to 0. So when you simplify this, you will end up with a, what you call a quadratic equation, that is lambda square minus 10 lambda minus 90 lambda plus 900 is equal to 0. You get the quadratic equation like this. So the essentially it is lambda is equal to 10 or lambda is equal to 90. The eigenvalues of the matrix A transpose A are given by lambda is equal to 10, lambda is equal to 90. Eigenvectors are lambda is equal to 90. So A transpose times of A minus lambda I, which will be equivalent to 74 32 32 26 minus 90 times of 1001. So which essentially will become minus 16 32 32 minus 64. Now reduce this matrix interchanging the rows R1 R2. So that means 32 32 will be on the main diagonal, minus 64 minus 16 will be on the subdiagonals. So when you write this R2 plus 2R1 and replace it as R2, so this anyway this should be R2, that is 1 by 2 R1. So this should be 1 by 2. So R2 plus 1 by 2 R1. So that is minus 16 plus 1 by 2 times of 32. So it is minus 16 plus 2 times of, so 1 by 2 times of R1. So that is anyway 16. This is okay, fine. And second one will be 32 plus 1 by 2 times of minus 64. So 3 2 is 31. So this also will become 0. Fine. So this is actually, there is an error. It is 1 by 2, not 2. The system associated with the eigenvalues lambda is equal to 90. So lambda is equal to 90 becomes, that is A transpose A minus 90I multiplied with x1 x2. That will be equivalent to 1 minus 2 0 0 multiplied with x1 x2, that is equal to 0 comma 0. So therefore x1 is equal x1 minus 2x2 is equal to 0, x1 is equal to 2x2. Let x2 is equal to 1. Therefore eigenvectors corresponding to the eigenvalue lambda is equal to 90 is v1 is equal to, that is v1 is equal to 2 comma 1. Similarly, the eigenvector corresponding to the eigenvalue lambda is equal to 10 is, that is v2 is equal to minus of 0.5 and it is 1. So normalizing the vector, it will give you, that is v1 is equal to, that is 2 upon 2.23607 minus of 0.5 upon, that is 1 upon 2.23607. So you get this matrix. Similarly, v2 turns out to be minus of 0.5 upon 1.11803 1 upon 1.11803. So we will end up this matrix. So ultimately you will have A is equal to U times of sigma V transpose. This is the matrix which you get it by using this transformation. And where this form of omega is nothing but, that is square root of 90, 0, 0 and square root of 10, 0, comma 0. So it turns out to be this matrix 9.486838 0 0 3.162278 0, comma 0, and this turns out to be of this form, that is V is equal to V1 and V2, and which will be equivalent to 0.89443 minus 0.44721, 0.44721, 0.89443. So you get a matrix using this form, and U is equal to 0.70711 minus 0.70710, and second row is 001, third row is 0.70711, 0.70712, and it is 0. You can also verify the solution, that is A is equal to U of sigma V transpose, where U is nothing but, U sigma is nothing but, that is 70711 minus 0.0710, 00, and it is 1, 0.70711, 0.70712, multiplied with sigma, and this is the matrix, and rest are all zeros. So you will have the matrix like this: 6.70806 minus 2.236069 00, 6.70826 2.236069. So when you multiply this matrix, U cross sigma multiplied with V transpose, this turns out to be 6.70826 minus 2.236069 00, 6.70826 2.23609 multiplied with the matrix, that is V, that is 0.894431, 0.447216 minus 0.447216, 0.894431, and essentially you do get as 7.00033, 1.008, 00, 5.0022, 5.0026, which is approximately, you can write it as 7105, 5. This is the matrix A. Thus, first solution is possible as we did it in the calculation. When it comes to the second solution, that is A is equal to U times of sigma V transpose, that is U cross sigma is 0.707108 minus 0.707098 0, 001, 0.707106, 0.707117 0, multiplied with sigma, that is 9.486833, 3.162278, and these are all 0, rest are all zeros. So this is 6.708216 minus 2.23606 00, 6.70817, 2.2361. So when you multiply this matrix, this you do get it, this matrix. So essentially this is 71005, 5. And there are many more methods in the similar fashion. one could also look into what we call the Gauss-Seidel iteration method, as we did many more examples. Solve the following system using Gauss-Seidel iteration method. Let's say you are given as a 3 equations, the first equation, second equation, third equation. There are 3 unknowns, x, y, z. So let's say that the initial guess x0 is being given as 1, 0, 1. So from the above equations, we have the formula, that is x of k plus 1 will be equivalent to 1 by 12 times of 1 minus 3 y of k plus 5 z of k. Similarly, the second equation is y of k plus 1 is equal to 1 by 5 28 minus x of k plus 1 minus 3 z of k. And similarly, z of k plus 1 is equal to 1 over 13 76 minus 3 x of k plus 1 minus 7 y of k plus 1. So when you simplify this, y1 is equal to, you do get as a 4.9 and z1 you do get as a 3.0923. And when it is second iteration, so your x2 will be 0.1468 and your y2 will be 3.7153 and z of 2 is 3.8118, and when you come to this third iteration, you do get x3 is equal to 0.7428. And similarly, this y3 is 3.1644 and z of 3 is 3.9708. So essentially you get x3, y3, z of 3, that will be equivalent to 0.7428, 3.1644, 3.9708. So in the fourth iteration, so you get x4, y4, z of 4, that will be equivalent to 0.9468, 3.0281, 3.9971. So you do get these equations. So therefore the x4, y4 and z of 4. Similarly, when you do the fifth iteration, so you do get x5, y5, z of 5. So this should be equivalent to, so from this equation you do have 0.9918, 3.0034, 4.0001. So this is the x5, y5 and it is z of 5. Similarly, when you do the sixth iteration, it is expected that the solution need to improve further. So you will have x of 6 as 0.9992, y of 6 as 3.0001 and z of 6 as 4.001. So as we see, if you observe very closely, the solution is getting stabilized, not much difference could be seen. That means the solution is going to have a best approximation. Similarly, as a matter of curiosity, if you do seventh iteration, 1 by 12, 1 minus 3, previous value, plus 5 into previous value, which turns out to be 1, right? That means x of 7 is equal to 1. And y of 7, and you do it 1 by 5, 28 minus 1, minus 3 into 4.001, which is 1 by 5, 14.9996, which turns to 2.993. That means y7 is approximately equivalent to 3.0. Similarly, z7, 1 by 13, 76 minus 3 times of 1 minus 7 times of 2.9999. So which is 1 by 13, 50 point, which is exactly 4. So that means you will have x7 is equal to 1, y7 is equal to 3, z7 is equal to 4. So therefore, the solution which we found is approximately close to the true solutions. So x is 1, y is 3, z is equal to 4. So that means what we learned from this lecture is when you keep on doing the iterations, so the solution gets stabilized, thereby error will be getting reducing and we should get a good approximation. So for the last 4 or 5 lectures we have seen several examples of iterative techniques. So I am sure that you might have got now comfortably you could be able to understand how iterative techniques could be used by using the floating point arithmetic of the numerical methods. So thank you very much for listening to my lecture. Thank you once again.